Good morning everyone. So welcome to my YouTube channel Maths Doctor. So today we are going to see 20 lecture on Riemann integration. So let's start today's topic. Today we are going to study Riemann sum. Okay, this is important topic. Okay. So what is Riemann sum? Let F closed interval AB to R be a function. Okay. And P is equal to AX naught X1 Xn is equal to B, be a partition of closed interval AB. Okay. We consider RPF is equal to summation I goes to 1 to n FPI, okay, delta xi for x pi lies between xi minus 1 to xi. Okay. Okay. We consider RPF is equal to summation I goes to 1 to n FPI delta xi for pi lies between xi minus 1 to xi. Okay. We call RPF the Riemann sum of F corresponding to the partition P over closed interval AB. Okay. So note that remember that in remember that Pi belongs to xi minus 1 and Pi is arbitrary in xi minus 1 to xi. You can choose any Ti. Okay. For okay. In RPF. Okay. Remember that Ti belongs to and Pi arbitrary in, okay, in RPF. In RPF, Pi is arbitrary. Okay. So the definition of RPF is defined such that Pi is arbitrary in between xi minus 1 to xi. Okay. You always remember this. Okay. Now note that observation let F close interval AB to R be a bounded function. Okay, bounded function. When we define Riemann sum, we do not consider F to be bounded. Okay? But here we are taking F is a bounded function. Then LPF is less than equal to RPF is less than equal to UPF. Okay. Why? Let's see its proof. Because we know that for, here I will write for any partition P of closed interval AB. Okay. So for any partition P of any partition P is equal to B of closed interval AB, we have, so MI will be always less than FTI and FTI will be less than capital MI for DI to XI minus 1 to XI. Okay. And I is 1 to 2 up to N. Okay. So what we got actually? So we can multiply both the side by delta Xi. So this implies capital MI delta Xi less than FTI delta Xi capital MI delta Xi. Okay. For EI belongs to Xi minus 1 to Xi. Okay. And I goes to 1 to. Okay. Now I can take sum. I goes to 1 to N. Mi delta Xi less than equal to summation I goes to 1 to and FTI delta Xi summation I goes to 1 to and capital Mi delta Xi. Okay. Now what is this? This is LPF. And what is this? This is RPF. And what is this? This is UPF. So this is true for any partition P of closed interval AB. Okay. Now we study what is called convergence of Riemann sum. What is how to define convergence of Riemann sum? Okay. convergence of Riemann sum. Okay. Let F close interval a b to R be a function okay. Then we say that the Riemann sum, we say that Riemann sum RPF converges to sum L belongs to, because Riemann sum are nothing but real numbers. Okay. So this converges to L belongs to R if given any epsilon greater than 0, there exists delta greater than 0, such that summation I goes to 1 to n f t I delta x I minus L is less than epsilon for any partition P is equal to a x naught x1 of closed interval a b with norm less than delta and for all pi belongs to xi minus 1 to xi closed interval okay. I goes to 1 to n. Okay. So this is the definition of convergence of Riemann sum. Okay. Convergence of Riemann sum. Okay. So note that one thing. If on sum RPF converges to L, we write limit norm P tending to 0 RPF is equal to L. So this is the notation. Once Riemann sum converges to L, we write this convergence like the limit norm P tending to 0 RPF is equal to L. Now we define what are the integrable function of Riemann integral function in terms of Riemann sum. So definition one. So the definition. Let F closed interval a b to R be a function. Then said to be Riemann integrable or just integrable or integrable if integrable over interval AB. Over closed interval AB. If RPF converges. If RPF converges to some L. So we are writing only RPF converges. It means it converges to some L. Okay. So note that in this case we have limit non-p tending to 0. RPF is nothing but A to B FF df. And we call this limit integral. Okay. Integral A to B. Okay. Integral A to B. Okay. But we have already given a definition of Riemann integration. Riemann integral function. What was that definition? That was for bounded function. What was that definition? That lower integral and upper integral equals. Then function is Riemann integral. So we are saying this definition 2. Okay. Because we are defining another definition. Okay. So what was the definition 1? The definition was that one in upper integral is equal to lower integral. So we are recalling. Now recall previous definition of Riemann integrability. Or just integrability. Okay, so we are recalling the definition. What was the definition? Definition was, we are calling this definition 1. Okay, we already done this definition. We are recalling just. Let F closed interval AB to R be a bounded function then F is said to be Riemann integrable or integrable over closed interval AB if A to B lower integral is equal to upper integral. Okay. In this case, we write A to B fx dx is equal to A to B lower integral equal to upper integral. Okay. And call A to B FFDF, the Riemann integral of F over closed interval AB. Okay. Okay. So this is happening. Okay. So this is definition 1. So we already defined definition 1 when we were studying Riemann integration. Now we define Riemann sum, and we give another definition of Riemann integrability, or you can say integrability. So whether both the definitions are same, it means they are equivalent. We will see they are equivalent. Okay. So definition 1 is equivalent to definition 2. So theorem. So we are calling it as theorem. Okay. Definition 1 is if and only if definition 2. So both the definitions are same. We will prove it. Okay. We will prove it. First assume that definition 1 is true. Then we will show that definition 2 is true. Okay. Riemann sum exists and its limit is Riemann integral. Okay. So it means definition 1 is true means what? Definition 1 is true implies that F is Riemann integrable over closed interval AB. Okay. So given epsilon greater than 0, okay, there exists delta greater than 0 such that for any partition P is equal to A x0, x1, x2 and so on, B of closed interval AB with ln P less than delta, we have UPF minus LPF, UPF minus LPF is less than epsilon. Okay. Now we have that this summation we already know that always Riemann integral always lies in between this range A to B, this range. It lies between LPF and UPF. Okay. Let's say this equation number 1. Okay. And we have written in today's lecture in observation, what we have written that the RPF also lies in between this. And what we have shown that this RPF also lies in between days to LPF and RPF. But what is this? This is summation I goes to 1 to n FPI delta XI less than equal to LPF, okay, UPF, okay. Okay. So from 1 and 2, we have LPF, okay, less than equal to this sum, Riemann sum, okay, and Riemann integral A to B fx dx both lies in UPF and LPF. So these two lies in between LPF and UPF. So their difference will be less than the difference of UPF with LPF. Okay. So this implies that because these two things lie in between these two values. So this implies that summation I goes to 1 to n FPI delta XI minus A to B fx dx less than equal to UPF minus LPF. But this is already less than epsilon. So this implies summation I goes to 1 to n FPI delta XI minus A to B fx dx less than epsilon for any partition P is equal to A x naught x1 xn of closed interval AB with norm of P less than delta and for all Pi belongs to xi minus 1 to xi, I goes to 1 to n. So what does it mean? Given any epsilon, you go to delta. You take any partition of P of closed interval AB, norm less than delta, you take Pi in between xi minus 1 to xi. Then this absolute value summation FPI delta xi minus Riemann integral is less than epsilon. What does it mean? It means that RPF converges to A to B fx dx belongs to R. So this implies G with non P tending to 0, RPF is equal to A to B fx dx is equal to this. Okay. So this implies definition 1 implies definition 2, because this is definition 2. Now conversely, so one direction is done, that definition 1 implies definition 2. Now we'll show that definition 2 implies Definition 1. Conversely, assume that definition 2 is true. Okay, true. Then, so we will show that, first of all, we have to show that definition 1 is true. So for definition 1, we have to first show that f is bounded and lower integral is equal to upper integral. Okay? We have to show two things. So f is bounded. Okay. First of all, we are going to show that f bounded. F is bounded on closed interval AB. Okay. So we will do it by contradiction. If possible, suppose that f is not bounded on closed interval AB. Okay. If it is not bounded on AB, so we are taking this partition. Now take partition P is equal to AX0, X1, Xn is equal to B. Okay. Then AB is nothing but union of X0, X1, union X1, X2. Okay. Xk minus 1 to Xk and so on, then Xn minus 1 to Xn. Fine. So what is this? This is I goes to 1 to n xi minus 1 to xi. Okay. Now, since f is not bounded on closed interval in AB, this implies that if f is not bounded closed interval AB, it means it will not be bounded at least one subinterval. We get here exists K there exists K in between this such that f is not bounded on xk minus 1 to xk. Okay. Because if f is bounded on closed interval, it will be bounded on any subinterval. But if f is not bounded on closed interval AB, it means it will not be bounded on at least one subinterval. I am calling it is not bounded xk minus 1 to xk. Okay. Now, so we write RTF. So we write define Fp is equal to summation I goes to 1 to n. I is not equal to k. Okay. F xi minus 1 delta xi, and we define Fp delta xk for all p belongs to xk minus 1 to x. Now we have fixed base quantity pxi. Okay, we have fixed here pi here for I not equal to k, and we are taking variable t here. Okay, so these things are fixed and delta xk is fixed. So note that ft is not bounded on xk minus 1. Note that f is not bounded on xk minus 1 to xt because f is not bounded on xk minus 1 to xt because these quantities are fixed. These quantities, this part is fixed, and this is positive part, and this is variable. T is variable, so f is not bounded here. So obviously, capital F is not bounded on this interval. Okay. Okay. Now, since definition two holds. Okay. Okay, holds for epsilon is equal to 1. Holds. Definition 2 holds means what? Definition, we have limit non-p tending to 0 RPF okay is equal to L. Okay, exist. Okay, so exist. It means if the I will take a norm p tending to 0, then it will be, this will converge to L. Okay, so it means, what does it mean? Given epsilon is equal to 1, there exists delta greater than 0 such that for any partition P is equal to A x naught x1 xn is equal to B of closed interval AB with non-P less than delta. We have summation I goes to 1 to n f ti delta xi minus L less than epsilon is equal to 1. Okay. So this implies I will put those which I have selected. So this will be, I am taking this one. So for all Pi belongs to xi minus 1 to xi, we have this one. Okay. So I am taking Ci. Xi minus 1 to delta xi, I not equal to k. Okay. F t delta xk minus L. So I have taken particular Ei. I am calling this xi minus 1. I am taking the bound initial point of subinterval xi minus 1. So this is less than 1. Okay. So this implies what is this? This is nothing but ft minus L less than 1 for all P belongs to xi minus 1 to, sorry, xk minus 1 to xk minus 1 to xk. Okay. But this will imply ft. You can add and subtract. Okay, this will be less than ft minus L plus mod L. Okay. So what is this? This is nothing but 1 and this is L. So what we have? We have ft less than 1 plus norm, absolute value of L for all P belongs to xi minus 1 to xi. Sorry, xk minus 1 to xk. xk minus 1 to xk. Okay. So this implies f is bounded on, because this is fixed. So this implies f is bounded on xk minus 1 to xk, which is a contradiction, because we have already shown by assumption it is, we have that f is not bounded on closed interval. So which is a contradiction. Which is a contradiction. Okay. Hence, f is bounded on, which is contradiction, as f is unbounded, not bounded on xk minus 1 to xk. Okay. So f is bounded on xk minus into xk. Okay. So we have shown that f is bounded. Sorry. So this is contradiction. This is a contradiction. F is not bounded on xk minus 1 to xk. So hence our assumption that f is not bounded on closed interval AB is wrong. Hence f is bounded on. Hence f is bounded on closed interval AB. Okay. So we have shown that f is bounded. Now we will show that f is Riemann integrable. Okay. Then our definition 2 will imply definition 1. Okay. So we have to show that f is Riemann integrable now. Okay. Since limit non-p tending to 0 RPF is equal to L. Okay. For any epsilon greater than 0, there exists delta greater than 0 such that for any partition P is equal to A x0 x1 up to xn is equal to B with non P less than delta, and for all Pi belongs to xi minus 1 to xi, we have summation I goes to 1 to n f Pi delta xi minus L less than epsilon. You expand this, what you will get? Minus epsilon summation I goes to 1 to n f Pi delta xi minus L less than epsilon. Okay. So this implies L minus epsilon less than summation I goes to 1 to n f Pi delta xi L plus epsilon. Okay. For all Ti belongs to xi minus 1 to xi. Okay. So this implies so L minus epsilon will be less than. Now if I will put a small mi in place of fti, then this will decrease. Okay. This will decrease. If I put capital Mi delta xi, this will increase and this will be less than epsilon. Why this will not be less than equal to? Because we have a complex set. If something is greater than this, the infimum will be also greater than. Okay. because we have compact set. Okay, or you can take equality here also. Okay, sorry, it can be sorry for my statement. It can be equal also. Okay, so we can take, in that case we can take epsilon by 2 here. Okay, no problem. So I am writing strict inequality there. Okay, so this is equal to this. So what we have, L minus ln less than, what is this then? What is this? This is LPF. So we can skip this one because this is greater than this, and this is UPF. This is UPF. So middle thing we can skip. So this is less than this, and this is less than L plus epsilon. Okay. So this can be equal also. Okay, no problem. So we can write here this one. Okay. So what we have? So what we will do? We will go and take here epsilon by 2. Okay. So in starting you take epsilon by 2 here. It will be epsilon by 2, epsilon by 2. It will be epsilon by 2. It will be epsilon by 2. Okay. So it will be less than epsilon by 2, less than epsilon by 2. So finally what we got? We got the difference of UPF minus LPF will be less than difference of base 2. L minus epsilon by 2 and L plus epsilon. So this implies UPF minus LPF is less than equal to L plus epsilon by 2 minus L minus epsilon by 2. So this is equal to L plus epsilon by 2 minus L plus epsilon by 2. So this is epsilon by 2 plus epsilon by 2. Okay. Okay. So you can take epsilon by 4 here. It will be better, no problem. So I am taking epsilon by 4 here. You replace epsilon by 2 by epsilon by 4. So replace, so write epsilon by 4 in this starting. So 4, 4, 4. So this is 4 here, this is 4, this is 4, this is 4. Okay. So finally what we got here will be epsilon by 4. So this is epsilon by 2. So what we have? UPF minus LPF is less than equal to epsilon by 2, but it is strictly less than epsilon. So this implies UPF minus LPF less than. Okay. Now, what we have? So given any epsilon greater than 0, there exists delta greater than 0, such that for any partition P of closed interval AB with known P less than delta, we have UPF minus LPF is less than epsilon. So what does it means? F belongs to RAB. Okay. So finally what we got? Definition 2 implies definition 1. Okay. Finally, the equivalence of definition 1 and 2 is proved. Okay. So we have first proved that f is bounded, and then we have proved that function is Riemann integrable. Riemann integrable means in the terms of definition 1 that lower integral is equal to upper integral. So definition 2 implies definition 1. Okay. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much. We will see you in next lecture.